Okay. Are you guys seeing this?
Yep.
Okay. All right. Yeah. So I think maybe that's a good way to sort of break down this discussion. Maybe a quick overview of Nova, and then maybe we can get into SuperNova itself and all the things that SuperNova changes to be able to handle virtual machine execution. So maybe a good place to start is just talking about, what is IBC and what do we hope to achieve with IBC, right? So I assume maybe some familiarity with IBC, but maybe we'll start with that, right? So at a very high level, IBC just concerns proving statements of the form where you want to apply a single function f many times recursively to some initial input, and you want to prove that this execution was done correctly, okay? A little bit more formally, we do also care that this function f takes as input some additional witness alongside in each invocation. This is how you can sort of prove knowledge of some secret input to this overall execution. Okay, so that's the overall IBC computational model. Do you guys have any questions before I move on to specifically how Nova targets writing proofs for IBC? Okay, so specifically, Nova is built on this line of works that studies how to write proofs for incrementally verifiable computation, originally introduced by Valiant. And the core idea is that, okay, well, to prove this original IBC computational model, you can do something like immediate, just write a quick circuit, yeah, like a huge circuit that just sort of bakes in all these computations F, right? And just prove the correct execution of that, right? But the problem is you can't, like, you pretty much have to unroll the number of loops you apply to F ahead of time. And, the circuit is huge, and that could lead to like a lot of blowups down the line. So really one of the ideas that Valiant came up with was that, okay, well, maybe what we can do is just write a proof for just a single iteration of F, and then cheaply update this proof as we keep iterating F. Okay, and the two core requirements of IBC are that as you keep updating F, essentially the proof size doesn't grow, right? Because then trivially you can just keep appending to the proof, you can keep iterating this proof as many times as possible. So the core idea of IBC is how specifically do we achieve such a primitive? How do we keep incrementing this proof without growing the size of this proof? Okay, and maybe before I get into Nova specifically, I'll briefly talk about what Valiant does to solve this problem. Okay, and what Valiant does is that, okay, to basically iterate this proof, the core idea is that instead of proving the function f itself, you prove an augmented version of f, in which you not only run f, but you also verify a proof which presumably attests to all prior iterations of f, okay? And the thing is, well, if you can prove the correct execution of this computation f right here, this latest iteration, you're proving not only that the latest iteration of f was run correctly, but also that all prior iterations, there exists a proof that attests to all prior iterations, okay? And therefore now a snark proof of this latest computation f essentially means that you have a proof that you've recursively built up for all I+1 iterations of f prime. Okay, so this is Valiant's original approach for taking a proof of I steps that's also very small and succinct and cheaply updating it into a new small and succinct proof of I+1 steps. And this is where we get this sort of core recursive step that is common to protocols such as Nova. So there are a couple of drawbacks to Valiant's work, which we discuss in Nova and previous talks. But basically, the core idea is snark proofs are quite expensive in practice to verify in a circuit. And that's why modern approaches are quite different from the original approach. So are there any questions about Valiant's original approach before we get into Nova itself and the folding scheme? Okay, so let me move on. Let me see if I added any slides. Okay, yeah, so the way to look at Nova specifically is, well, from a SuperNova perspective, Nova is just an IVC for a single instruction, right? And maybe I'll get into what an IVC is down the line, but for now, we can imagine IVC is just, let's just constrain ourselves to if we want to just run a single instruction in each step, okay? So how specifically do we do that? Okay, so previously what we were doing is we were running a single, we had a proof and we kept updating it using Valiant's technique, right? But one of the ideas that Nova comes up with that is like sort of inspired by like other approaches also, like the originally introduced by Halo, is that instead of checking the proof directly, we just basically don't even talk about a proof, okay? And instead, we just have a claim, and instead of checking this claim, we just defer it for later. And that's really where this folding scheme step comes in. Okay, what the fold does is allow you to defer a claim for later. Okay, so specifically what happens is assume instead our IVC proof consists of claims, okay? And basically there's a claim for the latest iteration of f prime and also another claim for all prior iterations of f prime, okay? So, all I minus 1 steps, okay? And what we do is we take this latest claim and fold it into this running instance for all prior iterations of f prime, okay? And then this computation f prime now outputs a new claim, okay, that claims the correct execution of I steps of the entire execution of f prime, okay? And now we make another claim that claims not only that this function f was run correctly in the latest step, but also that this previous claim for I steps was computed correctly as well, okay? So now the core invariant we maintain is that, well, if you can check these two claims, with respect to some witness, that you have a witness for the claim for the latest iteration of f, as well as a witness for all prior claims of f, okay? Then you essentially have a way of checking this IVC proof, okay? And now what the folding scheme allows us to do is basically allows us to keep compressing the witnesses for all these claims such that they don't grow in size over time, okay? So this is just a high-level overview of how folding is specifically used in IVC, or at least in Nova's IVC scheme. Do you guys have any questions about this high-level overview in particular? Okay.
Sorry, so
yeah,
the claims are kept a constant size, right?
Yes, that's precisely. So we can almost imagine that folding is a magical black box that takes two claims of the same size and outputs a single claim of the same size, okay? And now the question is, how specifically do we do that, right? So like, how do we fill in that black box in a way it's reasonable, right?
One question, what's the difference between claim and the proof?
Sure. So a claim you can think of as sort of an instance, okay, in some sort of relation, which you want to supply a witness for to prove that this claim is done correctly. So in R1CS, maybe this is like a popular NP-complete constraint system. Your instance is just going to be your constraint matrices and basically your public IO. Right, and your witness is going to be the rest of like the witness, the trace of the computation, which proves that this R1CS instance is satisfiable. Okay, so your claim is just maybe like a bunch of matrices or a bunch of polynomials, which encodes the computation that you're interested in.
So to add some more things, I guess one way to think about this claim is that you can think of, at least in concrete terms, it's just a commitment to the actual satisfying witness or purported satisfying witness. Whereas if you're thinking about a proof, you're going to commit to this witness, also run some polynomial IOP like Planck or Spartan or whatever. So that's like many more like multi-exponentiations or many more other operations, sum checks or FFTs or other things. So here to produce these claims, all you're doing is just commit to the satisfying witness. You're not doing anything more than that. So in terms of, I guess, the computation that the prover is doing to produce these claims, it's just commit to the satisfying assignment.
Yeah, great. Thank you.
Okay. All right. Yeah, so just really quickly to recap, all we're doing with Nova is that our IVC proof is actually just going to be a collection of claims, and then associated witnesses that the prover keeps track of separately, okay? And then this F prime computation essentially is compressing claims instead of checking them directly into a running claim, all right? And basically, we maintain this invariant that, like, you know, instead of checking the previous two claims, we check the next two claims instead, and that is enough to check all prior iterations of this computation F prime. Okay, so right, what do we fill into that forward box, right? How do we actually achieve that, right? And what we do in Nova is actually relax it quite a bit, and we say, okay, well, instead we're going to be working with an interactive protocol, which we call a folding scheme, okay? And then we're going to try to squeeze that back into the original Nova construction, okay? And hopefully everything should work out, right? So at a very high level, the folding scheme is an interactive reduction from the task of checking two claims in a relation to task of checking just a single claim in that same relation, okay? So syntactically how it works out is that the prover and the verifier take as input two claims, and the prover also takes as input the witnesses, just like a standard argument of knowledge. Okay, and just like a standard argument of knowledge, the prover and the verifier interact a little bit, okay, in the talk, and eventually the verifier outputs a new claim, which it believes is sufficient to check the two initial claims. Okay, and the prover on its end outputs the satisfying witness for that folded claim output by the verifier. Okay, and just like with an argument of knowledge, we can define meaningful notions of completeness and knowledge soundness, right? So completeness holds if, well, if the two input instances are satisfying, and we should have the output instance is also satisfying. And also knowledge soundness holds if, well, the output instance or essentially if some malicious prover is able to output a satisfying witness for the verifier's output folded statement, okay, then it must have known satisfying witnesses for the inputs to the verifier got as input to those two test statements, okay? And of course, we want to make sure that we don't call sort of trivial, quote unquote, solutions as folding schemes. You know, we don't want specifically the protocol in which the verifier just directly checks one of these instances to be called a folding scheme, right? So we want this efficiency requirement that, like, proceeding with this folding procedure should be significantly cheaper than directly having to check one of these witnesses. Okay, and that sort of all put together gives us the shape of a folding scheme. Okay, and really the question is, well, there's two questions. One is, how do we develop a folding scheme for NP, which I'll motivate in a second, right? And the second is, how do we shoehorn this back into our initial construction for Nova, right? How do we use this to fill in that black box for Nova? Okay, so does anyone have any questions about the shape of a folding scheme before we move on? Okay, so basically the core observation with folding schemes is that while we can just make these non-interactive using the Fiat-Shamir transformation, just like we do with normal arguments of knowledge, okay? And once we do that, we can sort of fill in the original thing we wanted to fill in with Nova, right? So specifically what's going on is that in this computation F prime, it's running the folding verifier, okay, which is taking care of folding these claims in a verifiable way, okay? And on the side, the prover's keeping track of these witnesses, all right, using the folding prover. And additionally, this folding prover has to send a sort of transcript or a non-interactive proof to the folding verifier, and that's completely fine because this computation F can take as input some additional non-deterministic advice, right? And the core invariant we have with folding schemes is that, well, the size of these witnesses do not grow over time. So that capital WI plus 1 is the same size as WI and capital WI, okay? So essentially, at a high level, what we need is that, well, if these claims are powerful enough to encode NP instances, okay, then they're powerful enough to encode statements about the computation F prime itself. And then the witnesses are just sort of these computation traces or other sort of objects that sort of attest to the fact that this computation F prime was run correctly. Okay, so at a high level, this is how we use a interactive folding scheme turned non-interactive to be able to build Nova, okay? And I guess the next thing to talk about, of course, is how do we achieve a folding scheme for NP? But does this specific architecture make sense so far? Okay. All right, yeah, so I'll move on then to how specifically can we build a folding scheme for NP, right? And this is mainly Nova itself. I'm not really sure how much we want to get into it, and how much we want to reserve for talking about SuperNova specifically. But maybe I'll start giving a high-level overview, and if you guys feel like I'm getting into too much of the details, we can maybe move on into SuperNova itself, okay? So specifically, right, one of the core observations here is, okay, what's a good language in NP such that we can fold two instances efficiently, right, into a single instance of the same size? And R1CS is a great starting point, right? Because R1CS essentially is a very simple sort of constraint system, but is also very expressive. And folding R1CS instances seems to be sort of natural because R1CS instances are only specified using matrices and vectors and so on and so forth. And because of that, we can think of folding as just taking random linear combinations of R1CS instances, right? But the core issue is actually with R1CS, there are, if you try to directly fold two R1CS instances, you end up with this issue where you start getting a bunch of cross terms, and you really you can't take a trivial random linear combination of R1CS without sort of breaking the equality of both sides of the equation. Essentially, is the core issue with that. Okay, and so to fix that, what we end up doing is sort of extending R1CS to get this notion called relaxed R1CS, okay? And a relaxed R1CS instance is more or less the same as R1CS, okay? Except specifically, it contains a scalar U, okay? As well as an error vector E, okay? So the full, basically, a witness W is satisfying if for the vector Z, which is equal to W plus X, X is sort of the public IO of the R1CS instance, and U is some sort of scalar. We have the AZ times BZ is equal to U times CZ plus this error vector E, okay? And, if you set U is equal to 1 and E is equal to 0, this is just a standard R1CS constraint system, okay? And like from previous examples, or previous papers, we know that R1CS can be used to encode like arbitrary arithmetic circuits and many other sort of very nice structures very simply in this sort of constraint system. Okay, at a very high level, each like row of the ABC matrices can encode basically one constraint, and that Hadamard product right there. When I say times, I mean Hadamard product allows us to sort of check a single multiplication for these constraints. Okay, so does anyone have any questions about R1CS or specifically relaxed R1CS? Okay. All right. So I guess the next step now is to discuss how specifically can we fold relaxed R1CS instances, right? And if we achieve that, then going up the stack, basically we achieve a folding scheme for NP, which allows us to achieve basically Nova, which allows us to achieve efficient IBC. Okay. So this is just in a single slide what it looks like, and it's a lot in one slide, but maybe I can go through each piece and we can maybe discuss any questions you guys might have, right? So one of the first things we do is we say, okay, well, we're not going to try to fold two relaxed R1CS instances directly. Instead, we're going to fold a version where you have committed to the witness and this error vector in the statement itself, and then you basically remove the verifier, like you make sure the verifier doesn't have to look at the error vector or the witness directly, okay? And essentially that preserves succinctness and also down the line allows us to achieve zero knowledge if needed, okay? And essentially the question is, okay, how do we fold two instances of this form? Okay, so what we have now is the instance consists of ABC matrices, a commitment to the error vector E1, U1, which is a scalar, and then commitment to the first witness W, which is the W1, okay, and then the public IOX1. And you have another one with just like E2, U2, W2, and X2, right? So the question is now the verifier sees these two instances. How does it compress these two instances in such a way that it gets a new instance of the same size, but checking this new instance is equivalent to checking the two initial instances? And at this point, it's more or less a bunch of math and like handling a bunch of cross terms, which end up showing up all over the place when you try to just take linear combinations of these terms, okay? And I don't think the details are incredibly interesting for SuperNova's purposes, but we can go into this if you guys are interested. So if you guys want me to go into specifically how this works, we can. Otherwise, you can just trust that, you know, doing math in this particular way gives us a new instance that is satisfiable in place of the original two instances. So any opinions on whether we should go into this or move on to SuperNova related things?
Actually, I'm quite interested how it works. Maybe a simple explanation.
Of course. Yeah, then we will take the time.
It may not need to take a long time, but just a simple explanation.
Sure, of course. Yeah, so if you recall sort of bulletproof style protocols, right? What do they do to, you know, bulletproofs does is this really cool idea, and like the precursor to bulletproofs, the inner pairing product or the inner product paper. Basically what they do is essentially take the task of checking the inner product of a vector and they split it into the task of checking the first half and the task of checking the second half, right? And what they do is they take a linear combination to fold it into a single task of checking a half size vector, right? But in this folding procedure, what they do is introduce a bunch of cross terms where, you know, you end up accidentally multiplying, you know, the commitment key of one half of the vector against, you know, like the other half of the vector, essentially, right? And you get all these cross terms, and what they do is send over commitments to these cross terms, and then the verifier uses these commitments to actually fold correctly, okay? And that is the core intuition for how the folding scheme for NP works, okay? We just make sure that we keep in mind what the cross terms would be, okay? And then we just basically, the prover commits to these cross terms ahead of time, and the verifier then just sends a challenge to fold against, and the verifier then computes a new folded instance with respect to these cross terms and the new challenge, right? So specifically, it turns out that roughly, if you wanted to just do like this sort of trivial folding, okay, where you just set u is equal to u1 plus r times u2 and x is equal to x1 times r times x2, and you also just set the witness to be w1 times r times w2, then if you end up just sort of taking this linear combination and sort of trying to equate both sides of the satisfiability check, you start getting all these cross terms, okay? And all of these cross terms are essentially just absorbed by this error vector E, okay? So the error vector basically, you can see it has the E1 term and also accounts for the cross terms in the middle and also accounts for this E2 term. So it accounts for both the previous error terms as well as the new errors that are generated by folding and handling all these additional cross terms. And the verifier essentially ensures that the prover computes this error vector and this witness vector correctly by computing a linear combination of the commitments over the witness vectors and the commitments over the error vectors. So one of the core assumptions we make is that we're working over additive commitments, okay? Or additively homomorphic commitments. And that essentially forces the prover to compute the new folded witness and the new folded error vector, okay? So that is sort of the core idea. Basically, what we're doing is we're folding just like bulletproofs did, but we're extending these ideas to handle for general NP instances. And what that really entails is just handling a bunch more cross terms along the way and just aggregating all these cross terms into a sort of catch-all term, which is the error vector right there, which can hold on to all these cross terms for us. Okay. And it turns out we can sort of prove knowledge soundness with this protocol. So, you know, like all the terms, or this entire statement is computed like this, and then the verifier computes, or the prover computes the additional vector, the witness like this. And it turns out that, well, if, you know, the prover does know a satisfying witness for the verifier's output statement, then it must indeed know satisfying witnesses for the verifier's input statements, essentially. This is just a standard sort of knowledge soundness proof to demonstrate that. Okay, so hopefully that gives a little bit more intuition for how this works. I think in our talk for crypto, we do extend into this a lot more and have a lot more slides, specifically reasoning about how and why we achieve folding schemes for Rockstar 1CS and all the motivation for all the modifications we do for our 1CS. But for now, does this give like a high level overview of how our folding scheme works? Or do you guys want me to go into a little bit more detail?
Just a very quick question. So essentially for every step of the computation, or say every time you apply F, the prover does need to commit to these new witnesses along the way.
Yes, that's correct, but it doesn't need to send them over to verifier, if that was your question. It sort of computes these new commitments and then feeds it into the F prime value, F prime function.
Okay, I see. So the verifier's computation doesn't increase with it.
No, the verifier's computation does not increase in any way with the number of recursion depth.
Thanks.
Yes. So maybe extending into that just a little bit, right? So in this interactive setting, what we would assume what's going on is that, every time the prover comes up with a new instance witness pair, it sends over the commitments to the verifier, right? And indeed, that sort of is what ends up happening. But in the non-interactive setting with this computation F prime, where the verifier is being run internal to the prover's sort of like execution of F prime, those commitments are sent directly to the folding verifier. So this capital UI term, this lowercase UI term will contain those commitments. So the prover basically keeps track of these commitments itself and proves that, okay, well, I have checked these commitments on your behalf in each recursive step. Okay. All right, so any other questions about how folding itself works before we get into maybe the details of SuperNova itself? And if you didn't follow all of the details of folding, it's completely fine, because really in SuperNova, we just treat it as a black box. All you need to understand is that we take two instances of the same size and compress it into a single instance of the same size. Okay. All right, so should we move on to SuperNova specifically and the computation model we support in SuperNova then? Okay, cool. All right, so what do we achieve with SuperNova? And Srinath, like if you wanted to chime in, this would also be great. But like basically, the core idea of SuperNova and what it extends upon Nova is that, well, Nova itself theoretically can handle virtual machines already, right? And just like with prior works, right? What we could do is just encode the entire universal circuit that encodes all of the instructions, and basically in that function F, and basically just run this like gigantic chip or virtual machine in each round, right? But the issue with this is that essentially you have to pay the cost of all the instructions in each recursive step, okay? And on the flip side, the other dominant approach for solving these sorts of issues is works like Buffet, which allows you to not have to pay in the cost of all instructions in each recursive step, but you sort of have to unroll the computation ahead of time, and you have to sort of keep track of the global computation instead of sort of only locally looking at how to update the computation in each step. Okay, so SuperNova really was a answer to try to put together the key benefits of both of these approaches, right? So with SuperNova, we said, okay, is there a way we can use recursion, but still only pay in the cost of the instruction used in each step? Okay, so specifically, if you have some program that runs add, then mul, then add, then SHA-256 or something like that, right? We only want to pay add for the first step, mul for the second step, add again for the third step, and SHA-256 for the fourth step, right? Instead of having to keep running SHA-256 in each recursive step, right? So that sort of is the motivation for SuperNova. And now the question really is, how do we formalize specifically the model of computation that we want? And how do we achieve that formal abstraction that we've built, right? So specifically, the abstraction we came up with is something called non-uniform IBC. Okay, and with non-uniform IBC, pretty much is like IBC, right? So recall that IBC just runs this function many times, but we allow this computation to dynamically choose which instruction is run next. Okay, so now these functions f sort of represent not the entire chip, but each individual instruction. So we can imagine we have L individual instructions and some sort of control function, which, in a RAM machine, this might be our program which decides what instruction to run next. Okay, and basically what we want is to prove that, okay, in the first step, we have we run the particular function associated with that program after it sees the witness in the initial input, and it chooses an index to run the particular first function on. And this first function outputs some statement zi, and you also might have an additional witness wi to feed into the second function. Okay, and the second function is now just going to be one of the L functions that is indexed by specifically what the program decides after seeing this omega value and this zi value, or z1 value. Okay, so basically in each step, this program, the phi, takes a look at the witness and the latest output and decides which of the functions in the instruction set to run. Okay, and we just keep doing this. Okay, and the statement that we're trying to prove is that, okay, well, if you sort of ran all these functions chained in this way, where we're dynamically choosing which function to run next based on the output of the previous function, then prove to me that this execution was run correctly. Okay, and that essentially is the core computation model that we support with SuperNova as opposed to Nova. Did you guys have any questions about specifically this computation model before we discuss how, at a high level, how we achieve it using SuperNova? Okay. All right. So I think the next step then is to move on to specifically SuperNova itself. Okay. So just a really quick recap. Recall that Nova looks something like this, where we were just folding into a running claim of all prior iterations. Okay. Now, one of the core properties that we require from folding schemes is that the structure of the two computations, so the structure of the running instance, as well as what we're the instance that we're trying to fold into it, has to be the same. All right. And what this manifests into is that we need both the instances of the folding scheme to have the same ABC matrices, which represents the same computation. Okay. So if we try to do the same trick with SuperNova, it turns out that, well, one computation can be talking about F1, another computation can be talking about F2, another one can be talking about F1 again. It starts it's unclear how to take a claim about F1 and fold it into a claim about F2, right? Or F1 and F3 and so on and so forth, right? So the core idea in SuperNova is that, well, let's not try to squeeze it all into one sort of running instance. Instead, what we're going to do is hold on to multiple running instances. Okay, and each of these running instances basically keeps track of a particular instruction. Okay, so U1 maybe keeps track of the first instruction of all prior invocations of the first instruction. U2 keeps track of all claims about basically the second instruction, and so on and so forth. And what SuperNova does is make sure that we can still efficiently compress into these lists of running instances. Okay, so that is essentially the core idea of SuperNova, right? What we do is roughly, right, instead of having to fold or deal with all of these claims in each step, we only have to deal with a single claim in each step, right? And what that means is that you only have to pay in the cost of that single claim you've made in that particular step using the folding scheme. Okay, so does this high-level overview make sense before I start digging into the diagram itself?
Sorry, I have a question regarding like the size of these claims.
Sure.
So they all see Z, right? The Z coming in and then back out.
These claims, so these claims specifically, this UI term right here, the latest iteration, this sees Z or Z.
Okay.
Right. And these guys right here, they see sort of like linear combinations of all prior Z's or like some subset of the Z's, but not directly this value right here. Okay.
Okay. But so then does that mean that they have to, like the circuits for each of these claims will be at least of size Z for each of them?
So the claims, yes, that will, because Z is in the public IO. Yes. So, but these claims are not circuits; they're just commitments to the witness plus some public IO built in. But yeah, Z will be put into there.
So in our actual implementation, these public IO is going to be hashed. So these capital UI, all those will just have, I think concretely it just has one hash, or when you're using cycles, it will have two hashes as the public IO.
Okay, like in Nova, like
Yes.
the same way you hash on hash every time. Okay.
Yes.
Thanks.
I guess one other thing that I guess is not depicted here is like the circuit is sort of here for simplicity. I guess we show it taking all of these running instances as input, but in reality, it's going to operate on only one of them. So you could use a Merkle tree or more sophisticated things like multi-set hashing. So you only need to retrieve just one of the running instances, whatever that gets used in the folding scheme. So the circuit doesn't really have to enumerate all the running instances.
I see. But if you have a Merkle tree, are you paying the cost in that F prime circuit?
Yes, yes. So for example, for
Yeah.
Merkle tree, it would
Okay.
pay log L hashes.
Yeah.
For multi-set hashing, it would be just a constant number of constraints.
Amazing. Thank you very much.
Okay. Yeah, but as Srinath said, for simplicity of discussion, we're just going to assume for now that this F prime value takes as input the entire array of claims. Of course, they can be compressed away. Okay, any other questions before I continue? Okay. Okay, so I guess this is sort of the technical part, like specifically, like at this point, it's just a bunch of wiring and making sure, all the terms are sort of updated correctly. But the core idea, okay, is that we're going to assume that this computation of prime takes as input, okay, a program counter, which sort of indicates what the index of the last executed computation is. Okay, so this PCI, okay, and also a claim that that last execution was run correctly. All right. In addition, it's going to take as input a list of running instances. All right. And each of these, again, like I mentioned, basically each of them tracks the correctness of all prior executions of a particular instruction. Okay. So now this PCI, I mean, like basically is used to decide, okay, which instance to fold this incoming fresh instance into. Okay, which of the running instances to fold it into, all right? And that's what this UI PCI value denotes. Or sorry, yeah, it just picks that one up, and then you fold it, okay, and then you get a new updated instance. And basically, the rest of the instances are copied over, and then just that updated instance is written into the specific index of this array initially, okay? And this is how you get a new list of running instances, okay? So the core invariant we want to maintain is that, well, okay, if checking this lowercase UI and checking all of these running instances is equivalent to checking I steps of the proof, then we should have that checking these running instances, the new updated running instances, plus a new claim of this latest execution is equivalent to checking I plus 1 iterations of the computation F prime, or of this an IVC computation, okay? And just like with Nova, the additional thing we do is we actually run the latest iteration of f in this computation f prime. And that means that this claim not only attests to the fact that all these new running instances were computed correctly, but also attests to the fact that the latest iteration was run correctly. Okay, and this we also have this the control function being run, and that basically takes as input this omega and zi as discussed before, and outputs this updated PC. And this is like basically this PC is going to be used as input to the next step, just like this PC was used as input to this step. Okay. Now you might be wondering, okay, well, what stops the adversary from just picking in some malicious PC, right? Like, you know, these are just treated as witness anyways, right? So the adversary can just put in some random PC. And really what stops that is the soundness of the folding scheme, right? Because if you just try to fold into some arbitrary running instance, then you'll break the correctness of one of these instances out here, okay? So that essentially is how this particular step works, okay? And that is pretty much the overview of SuperNova and essentially what it changes over Nova. Did anyone have any particular questions about the details of this?
So we work on the instruction level here, right? So we have L different instructions. I was thinking there may be some trade-offs in, you know, dividing the program into, say, bigger chunks. Obviously, that would make each individual subcircuit more complex, but you would need to do fewer steps. But then it seems like because you need these L different UIs, that wouldn't really be a feasible approach at all. Is that roughly accurate?
I think you could definitely do that. Like, for example, you could do even something higher level where, let's say you run LLVM or something, and you extract basic building blocks, and you build a custom sort of quote unquote processor that only can execute these basic building blocks. I think it sort of opens up like sort of building this application specific proof system where you can only invoke these building blocks, and those building blocks are doing exactly what you wanted them to do. I think you could do that, but I guess the only thing that you have to worry is like the cost of maybe for some applications it's useful to do it that way. For others, maybe it's different.
Do you have any more specific thoughts on the trade-offs with that? Like here, we're considering like the smallest possible steps with each instruction. Do you have any intuition or thoughts about what is the optimal way for something like LLVM, let's say?
Yeah, I think like, for example, one thing to look at is the recursion overhead, like the cost of doing everything below this purple box, the phi, like that's going to cost, at least if you're only folding one step at a time, like you're just doing the sequential version, it's about 10,000 constraints. So as long as the work that you're doing inside this F is at least those many constraints, I think you can mitigate the cost of recursion. But if you're doing more folds, like for example, I think one of the things we didn't touch upon in this or even in some of our papers is our computational model is sequential, but you can actually produce these proofs in parallel. Like we haven't described how to do this in our papers, but it's possible. So in that case, the recursion overhead is much higher, slightly higher, I think maybe 20,000 constraints. So I think as long as you make sure the work that each instruction does is at least the recursion overhead, I think you sort of don't pay a lot of, I guess you can tame the recursion overheads if you can keep it that way. Does that help?
Yeah, cool. Thanks.
I had another question that also applies to just the regular IVC setting, which is like the soundness error, and how does it compound with steps of the IVC like computation? And I've seen like some debate around it online, so I was a bit curious to hear your thoughts.
Sure. So when you say soundness error, I assume you specifically mean like knowledge soundness error?
Yes.
Sorry. Okay. Yeah. So yeah, this is actually like a big open question in this space right now with recursion specifically. So essentially, if you really dig into the proofs and you look at it, it turns out that like it sort of does blow up polynomially every time with every recursion step, right? Which means we sort of need to make assumptions about the nature of the computation to be able to say something meaningful about these soundness guarantees, okay? So specifically in Nova, what we end up saying, and also in SuperNova, is that we're going to assume there's some large constant, like we don't know of, or it could be some constant, but we have to assume for the sake of the proof that it is a constant, the number of recursion steps that we're taking, okay? In general, though, if you actually do want more than constant recursion depth, okay, you sort of have to make like basically either knowledge assumptions, okay? So what you would do with knowledge assumptions is say something like, okay, we're going to assume that, like, you know, the folding scheme extractor only has a constant overhead over any malicious prover over for the folding scheme, right? And if you make that sort of assumption, then like everything sort of goes through and you can like recurse the polynomial depth or as much as you want, right? But if you're not willing to make that sort of assumption, the other thing you can do is, as Srinath alluded, is we can sort of use a tree-like structure, okay, where the recursion depth is only logarithmic, okay, but we sort of fold using like a tree structure, and so we still get like a polynomial number of steps that we're considering, okay? And then you still have to make some sort of assumption, but it is still a lot better than just directly saying constant or just directly assuming an extractor with constant overhead, okay? So really at a high level, to answer your question, it really depends on what sort of assumptions you're willing to make and what sort of topology your computation has. And based on that, you can sort of bound the knowledge error.
That makes sense. And do we have like a ballpark estimate for that constant, like in concrete terms? Say like I'm using a field of size like, I don't know, 256 bits. Do we know like how many recursion steps I can make?
Yeah, so unfortunately, I don't think we do have a ballpark estimate for something like that. Maybe it can be computed, but I believe it is going to be difficult because we do a heuristic instantiation step, as with any other proof system for recursion nowadays, right? Where there is going to be like, so if you recall, we proved this folding scheme secure, right? And like here we can have like great like sort of concrete assumptions on like or concrete estimates for how secure the folding scheme is, right, in an interactive setting, right? But what we have to do to actually use it in IBC is we have to make it non-interactive using Fiat Shamir. And after we do that sort of step, we're just making assumptions on how secure the overall protocol is, right? Because we're using a concrete hash function instead of random oracle. Maybe we can just say something like, okay, well, the same soundness guarantees like carry over. Maybe not. It really depends on what you're willing to believe.
Okay.
But
Thanks.
by the way, I think so. Sort of this recursion depth is not specific to our construction. I think it applies to pretty much any recursive proof system that uses, I guess, the verifier as a circuit and then has the prover prove this. Yeah, and the other point is, I guess, like, Abhiram, can you go to the next slide? I think some of this debate was also about this error term itself. The error term that shows up in R1CS. I think
there was a misunderstanding there.
Yeah. So this error term does not like grow in any way. It's just
this fully agreed. Thanks so much. Okay, I don't want to be hogging the Q&A session, but so this is the part I was, I guess, very interested in is like, so you know how like in Nova you have this final proof compression? Are you planning on doing the same for SuperNova?
Yeah. Yeah, so we do already have like a zero knowledge layer for SuperNova. It's just not public yet. Hopefully we'll get it out at some point soon.
Wow.
But yeah, like it is possible to do something like this for SuperNova as well.
Yeah, getting zero knowledge was a little tricky, but I think we worked it out. It required some small tricks to get zero knowledge because in the SuperNova context there is some additional information that's revealed at each step. So we just needed some additional, I guess, techniques to make it hiding.
Yes, looking forward to that publication.
Hey, I had a question about memory. For memory, we can always use Merkle trees, but I think the paper mentioned a couple other techniques.
Yes. Yes, so there's this other technique. It actually dates back to 90s, based on multi-set hashing. So it was described in one of our earlier papers called SPICE back in 2018. It sort of uses, instead of keeping a Merkle tree, it uses something called incremental multi-set hash function. So it keeps track of the hash of the reads and hash of the writes. And then in the end, it also has this sort of like deferred verification where in the end, the prover has to prove that this read set was a subset of the write set. It can do that through the proof system itself. If that holds, it just means that all the prior reads and writes were done correctly. So the way we would use this technique is at each step, instead of the prover would just give us the running instance to the circuit, and we would keep track of this read set and write set digests, update them appropriately. And the cost of updating is, I think, a couple of hashes and maybe one, I guess, point addition. And in the end, the prover would just incur O of L cost, where L is the number of instructions, to prove that all the memory operations were done correctly.
Yeah, that sounds very interesting. I'll have to check out that paper. Are there any caveats, like any non-standard cryptography that it uses, or?
I think the main actually the technique compared to Merkle trees, it has better asymptotics. I think also better concrete cause. It also gives concurrency, like you can have multiple threads operate on it. Like you can have different proof systems sort of produce proofs in parallel, operate on the same memory. So it has all these nice properties. The only caveat is, so once the execution finishes, the prover has to prove a statement about the entire memory. So it's going to incur costs proportional to the size of the memory. I think that's the main caveat compared to something like Merkle trees, where every operation is logarithmic and you don't do anything like this at the end of the execution. But in our context, that work is just proportional to the number of instructions. So I think it's manageable in this context.
Okay, thanks.
Okay, do we have any more questions? Okay, looks like not. Well, I'd like to thank you both for joining us. Really interesting paper. I guess if there's no more questions, I'll see you all next week.
Thank you, guys.
Thanks
All right,
again.
well, thank you for having us.
Thank you.
Thanks. Nice explanation. Bye.
Thank you.